From the moment humans first looked up at the night sky, we've been haunted by a single, irresistible question: what lies beyond the stars? That longing to venture past the familiar glow of our own solar system, to cross the unimaginable gulfs between stars and touch the unknown, has burned in our collective imagination for centuries. Today, we stand on the edge of making that dream a reality. For the first time in history, the idea of interstellar travel isn't just science fiction. It's a challenge being tackled by scientists, engineers, and visionaries with ideas so bold, they'll rewrite everything we thought possible. Picture this: sleek spacecraft riding beams of light across the cosmos, or vast arcs carrying entire civilizations through the void over thousands of years. Some of these theories are grounded in cutting-edge physics, while others stretch the bounds of imagination, mysterious propulsion concepts that defy conventional understanding, alien megastructures hidden in plain sight, or even the wild possibility that we might not be the first to crack the interstellar code. These aren't just fantasies, they're real proposals being explored by some of the brightest minds on Earth, and whether they succeed or fail, they reveal something profound about our species. We refuse to be bound by the limits of our own world. This journey through 30 of the most astonishing theories about how humanity, or perhaps something else, might achieve the universe's first interstellar voyage, will take us from the edges of known science to the fringes of speculation. Some ideas will sound like they're pulled straight from a futuristic novel, while others might just be the blueprint for our future among the stars. But one thing's certain: by the time we're done, you'll never look at the night sky the same way again. So strap in, because we're about to dive into the most thrilling possibilities about how the first interstellar leap could happen, and who might already be out there waiting for us. What if humanity isn't the first species to dream of crossing the stars? The ancient alien hypothesis suggests that long before we even existed, other civilizations may have already solved the puzzle of interstellar travel, and some believe they left clues behind. From bizarre artifacts that defy historical explanation to ancient texts describing celestial visitors, there's a tantalizing trail of breadcrumbs that some researchers say point to extraterrestrial pioneers who mastered the cosmos eons ago. Take the famous Antikythera mechanism, a 2,000-year-old device found in a shipwreck off Greece. This intricate bronze gear system, capable of predicting astronomical events with startling accuracy, seems centuries ahead of its time. Could it have been inspired by, or even borrowed from, a far more advanced culture? Or consider the Dogon people of Mali, whose oral traditions describe the star Sirius with impossible precision, including details about its invisible companion star that modern telescopes only confirmed in the 19th century. How could an ancient tribe possess knowledge that defied their technological era? Then there are the pyramids, not just Egypt's towering wonders, but similar structures scattered across the globe, from Mesoamerica to Cambodia. The precision of their alignment with celestial bodies, their sheer scale, and the logistical nightmare of their construction with primitive tools have fueled theories that these monuments were built with extraterrestrial guidance. Even ancient texts like the Indian Vedas or Sumerian tablets describe flying machines called vimanas and gods descending from the heavens in fiery chariots. Could these be garbled accounts of advanced spacecraft? Skeptics argue that these mysteries have earthly explanations: human ingenuity, lost technologies, or simple myth-making. But the ancient alien hypothesis forces us to ask a provocative question. If another species did crack interstellar travel long ago, where are they now? Did they vanish, move on, or are they still out there, watching? Whether you find the evidence compelling or coincidental, one thing's clear: the idea that we might be following in the footsteps of interstellar pioneers adds an electrifying twist to humanity's own quest for the stars. Now imagine a vessel so vast it carries entire cities within its hull, a world unto itself, drifting through the blackness of space for centuries. This is the generation ship, one of the most plausible yet haunting concepts for interstellar travel. Unlike sleek rockets hurtling between stars in a human lifetime, these arc-like structures would move slower, their passengers resigning themselves to a sobering truth: they will never live to see their destination. Their children's children might if the ship survives the voyage. The principle is simple, even if the execution is staggering. A generation ship would function as a closed ecosystem, recycling air, water, and waste indefinitely while producing its own food through advanced agriculture. Think of it like Earth in miniature, hurtling toward another star at a fraction of light speed. Early designs propose cylindrical habitats rotating to simulate gravity, with forests, lakes, and even artificial weather to stave off the psychological toll of deep space. The goal: to create a stable society that can endure the millennia-long journey to places like Proxima Centauri or Tau Ceti. But here's where the concept gets thorny. Who decides who gets a seat on this ark? Would it be an egalitarian lottery, a wealthy elite, or a hand-picked group of scientists and engineers? And what happens if society aboard the ship fractures over generations? Mutinies, resource wars, or even the loss of the original mission's purpose could doom the endeavor entirely. There's also the chilling possibility that by the time the ship arrives, Earth might have developed faster propulsion, rendering the travelers obsolete, like pioneers arriving on foot after the invention of the airplane. Perhaps the greatest ethical question is this: is it fair to condemn generations to life in the void, all for a destination they didn't choose? Some argue it's no different from humanity's ancient migrations across continents, where parents embarked knowing their children would inherit the journey. Others see it as a form of intergenerational imprisonment. Yet despite these moral quandaries, the generation ship remains a compelling backup plan, proof that even without warp drives or wormholes, humanity's stubborn will to reach the stars could still prevail. If we're willing to pay the price, and that's the paradox at the heart of this idea, it's not a glamorous solution, no roaring engines or instant jumps across the galaxy. Just patience, sacrifice, and an unbroken chain of humanity stretching across the centuries. But in a universe that doesn't care about our lifespans, it might be the only way to plant our feet on alien soil, even if it takes 1,000 years to get there. What if the vast distances between stars aren't the impassable barriers we think they are? Imagine folding a piece of paper so two distant points touch. That's the essence of wormhole travel, a theoretical shortcut through the very fabric of spacetime. Unlike generation ships plodding across the void for millennia, wormholes promise something revolutionary: instantaneous leaps across the cosmos. The idea isn't just science fiction. It's rooted in Einstein's equations of general relativity, which describe spacetime as a flexible sheet that can warp, twist, and even tunnel through itself. But here's the catch: while the math allows for wormholes, nature doesn't make it easy. Natural wormholes, if they exist, would likely be microscopic, unstable, or hidden in the chaotic depths of black holes. Keeping one open long enough for travel would require something exotic like negative energy or matter with repulsive gravity, substances we've only theorized. Yet this hasn't stopped physicists from dreaming. Some propose that an ultra-advanced civilization could stabilize a wormhole by threading it with cosmic strings, hypothetical remnants from the Big Bang, or by harnessing the energy of entire stars. And that raises a spine-tingling possibility. Could someone have already done it? Ancient myths speak of portals to other realms, gods stepping between worlds, or heroes vanishing into thin air. Might these stories be garbled accounts of wormhole encounters? Even more unsettling, if future humans ever master this technology, could they be the ancient astronauts of our past? The implications spiral outward. Wormholes wouldn't just connect distant places, they might bridge eras, turning history into a tangled web of cause and effect. Of course, skeptics wave away these speculations. Wormholes may forever remain mathematical curiosities, too fragile or energy-hungry to ever be practical. But the allure persists. If they're possible, even in theory, then the universe might be threaded with hidden doorways waiting for the right key to turn. And if that key was turned long ago by hands not our own, the cosmos could be far stranger and far smaller than we ever dared believe. Light sail propulsion turns the gentlest force in the cosmos, light itself, into an engine capable of crossing the void between stars. Unlike roaring chemical rockets or speculative warp drives, this method harnesses the subtle but unrelenting pressure of photons striking a vast reflective sail. Picture a spacecraft with sails thinner than a soap bubble, kilometers wide, catching the push of sunlight or targeted lasers to accelerate toward the stars. It's slow by sci-fi standards, but it has one irresistible advantage. It requires no fuel. Once deployed, a light sail could theoretically keep accelerating for years, even decades, building up enough speed to reach another solar system within a human lifetime. One of the most ambitious projects exploring this idea is Breakthrough Starshot, a plan to send a fleet of gram-sized probes to Alpha Centauri at 20% the speed of light. These tiny spacecraft, each no larger than a postage stamp, would be propelled by an Earth-based array of powerful lasers firing in unison, a beam so intense it could push the sails to interstellar velocities in mere minutes. The probes would carry miniaturized cameras, sensors, and communication equipment, beaming back the first close-up images of an alien star system. It sounds like fantasy, but the physics checks out. The real challenge isn't the principle, it's the engineering. A laser array powerful enough to pull this off would require gigawatts of energy, and the sails would need to withstand the brutal acceleration without tearing. Even a single dust grain colliding with a probe at relativistic speeds could vaporize it, yet light sails have already proven their potential. In 2019, the Planetary Society's Light Sail 2 mission successfully maneuvered in Earth's orbit using nothing but sunlight. Japan's Ikaros probe, launched in 2010, became the first spacecraft to demonstrate solar sail propulsion in interplanetary space. These early missions are mere whispers compared to the interstellar ambitions of Starshot, but they prove the core idea works. The universe has been bathed in starlight for billions of years. Why not use it as a highway? There's a poetic symmetry to this approach. For centuries, humanity relied on wind to cross oceans. Now, we might harness light to cross the cosmos. But the limitations are sobering. Light sails excel at sending small, fragile payloads, not crewed ships. Deceleration at the destination is another puzzle. Without a laser array at the other end, stopping becomes nearly impossible. And then there's the haunting question of time. Even at 20% light speed, a probe would take over 20 years to reach Alpha Centauri. By the time it arrives, the civilization that launched it might have moved on to faster, better technologies. Still, light sails represent something profound, a bridge between the possible and the fantastical. They don't demand exotic physics or cosmic miracles, just patience, precision, and the audacity to turn starlight into an engine. In a universe where distance is the ultimate obstacle, even the faintest push might be enough to carry us forward. Forget generation ships and light sails. What if the answer to interstellar travel isn't about speeding up the journey, but slowing down the travelers themselves? Cryogenic suspension, the science of freezing living organisms to halt biological time, offers a radical alternative to centuries-long voyages. Imagine crews sealed in pods, their hearts stopped, their brains silent, preserved in icy stasis until the ship reaches its destination decades or even centuries later. It's a concept ripped from the pages of sci-fi, but with roots in real-world science that might just make it feasible. The principle sounds simple enough. By cooling the human body to temperatures below -196 degrees Celsius, biological activity grinds to a near-complete stop. Cells no longer divide, chemical reactions freeze mid-process, and decay effectively pauses. In theory, a traveler could be revived centuries later with no memory of the passage of time, like hitting pause on a movie and resuming it years later. But the reality is far messier. The human body isn't a single substance, it's a complex mosaic of tissues, each reacting differently to extreme cold. Ice crystals forming in cells can shred them like microscopic shrapnel, while the very chemicals used to prevent freezing can become toxic at low temperatures. Today, cryopreservation is already used to freeze embryos, sperm, and even small patches of tissue for medical purposes, but whole body preservation remains out of reach. Companies like Alka and the Cryonics Institute offer post-mortem freezing for those hoping future science might one day revive them, but these procedures are controversial, more a leap of faith than a proven technology. Even if revival were possible, the psychological toll of waking up in a foreign century with everyone you ever knew long dead raises ethical questions we're barely equipped to answer. Yet the potential is too tantalizing to ignore. Paired with slower propulsion methods, cryogenics could turn interstellar travel from a multi-generational odyssey into a single-generation leap. A ship carrying frozen passengers wouldn't need sprawling habitats or self-sustaining ecosystems, just enough power to maintain the cold. And unlike generation ships, there'd be no risk of societal collapse over centuries. The crew would remain unchanged, their knowledge and mission intact. The biggest hurdle isn't just freezing people, it's thawing them safely. Reviving a complex organism without cellular damage is like unfreezing a snowflake and expecting every crystal to return to its original shape. Some researchers propose nanotechnology as a solution, with microscopic robots repairing cell damage molecule by molecule. Others suggest replacing blood with cryoprotectants, synthetic fluids designed to prevent ice formation entirely. These ideas hover on the edge of possibility, teasing a future where death itself might be negotiable. And then there's the eerie question lurking beneath it all. If we master suspended animation, could others have done it first? Ancient myths speak of heroes sleeping for centuries, gods resting in hidden tombs, or entire civilizations vanishing only to return in times of need. Could these stories be garbled accounts of a lost technology, or worse, evidence that someone else is already out there, frozen and waiting to wake up? Cryogenic suspension forces us to confront the very nature of life, time, and identity. It's not just a transportation method, it's a philosophical gambit, betting that the future will solve problems we can't yet fathom. Whether it's humanity's best hope or a pipe dream wrapped in liquid nitrogen, one thing's certain: the line between death and dormancy has never felt so thin. Time dilation might sound like the stuff of science fiction, but it's one of the most mind-bending yet scientifically valid ways interstellar travel could become a reality. Einstein's theory of relativity tells us that time isn't the constant ticking clock we experience, it's elastic, stretching and compressing depending on how fast you're moving. If a spacecraft could accelerate to a significant fraction of light speed, something extraordinary would happen. While centuries might pass on Earth, the travelers aboard the ship could experience only a few years. This isn't just a thought experiment, it's physics. Take the famous twin paradox. Imagine two identical twins. One stays on Earth while the other boards a starship bound for a distant star at 90% the speed of light. From Earth's perspective, the journey might take decades, but for the traveling twin, time slows down dramatically. Upon returning, they'd find their Earth-bound sibling aged far more than them. This effect isn't hypothetical, it's been measured. Atomic clocks flown on jets tick slightly slower than those on the ground, proving time dilation is real, even if the difference is minuscule at everyday speeds. Now imagine applying this to an interstellar mission. A ship traveling at 99% light speed could reach Alpha Centauri in just over 4 years from the crew's perspective, even though over 4 years would still pass on Earth. The real magic happens with longer voyages. At these speeds, a trip to a star 2,000 light-years away might feel like only a few decades for the travelers, even if 2 millennia unfold back home. That's the tantalizing promise of relativity, crossing impossible distances without outliving your own lifespan. But here's the catch. The energy required to accelerate a ship to such velocities is staggering. Even with perfect efficiency, pushing a human-sized craft to 99% light speed would demand more energy than humanity currently produces in decades. And then there's the problem of cosmic debris. A speck of dust colliding with a ship at near light speed would hit with the force of a nuclear bomb. Shielding becomes a nightmare when every stray atom is a potential bullet. The strangest consequence, though, isn't technical, it's emotional. Time dilation means interstellar travelers wouldn't just leave Earth behind physically, they'd leave it behind in time. Returning home after even a short trip could mean finding loved ones long gone, societies transformed beyond recognition, or civilizations that no longer remember why the mission was launched in the first place. It's the ultimate one-way trip, not just through space but through history itself. Yet despite these challenges, time dilation remains one of the few methods of interstellar travel that doesn't require speculative physics. No wormholes, no warp drives, just the cold, hard math of relativity, and that makes it uniquely compelling. If we ever crack the energy problem, humanity might not need immortality to reach the stars, just a fast enough ship and the courage to watch the universe age without us. What if the secret to interstellar travel isn't better engines but more energy? That's the promise of Dyson Spheres, megastructures so vast they could enclose an entire star, capturing its every photon to power a civilization's cosmic ambitions. The concept, dreamed up by physicist Freeman Dyson in the 1960s, isn't just a sci-fi trope. It's a plausible roadmap for how an advanced species might leap from planetary to interstellar capability. Picture a swarm of mirrors, solar panels, or habitats encircling a sun, absorbing its energy not in drops but in oceans. With that much power, even the most energy-hungry propulsion systems, like antimatter drives or laser highways, become feasible. But how would such a thing even work? A full Dyson sphere, a solid shell around a star, is likely impossible. The engineering stresses would be unimaginable. Instead, most theorists imagine a Dyson swarm, a constellation of millions of orbiting collectors drifting in carefully balanced orbits. Each unit could be anything from a massive solar farm to a habitat filled with living beings, all feeding off the star's boundless energy. Over centuries, a civilization might mine their planets, even dismantle them, to build this colossal infrastructure. The payoff? Energy output measured not in gigawatts, but in the equivalence of entire planetary economies every second. Here's where it gets eerie. Astronomers have already spotted stars with bizarre, irregular dimming patterns like Tabby's star, whose light flickers unpredictably as if something colossal is passing in front of it. Could these be partial Dyson swarms under construction, or perhaps the ruins of one built long ago? The idea isn't as far-fetched as it sounds. If even one civilization in our galaxy mastered this technology, their home star might glow differently, leaking infrared radiation from the waste heat of their megastructures. Some researchers have scoured sky surveys for exactly these anomalies, finding a handful of candidates that defy easy explanation. The implications are staggering. A species with Dyson-level energy could reshape entire solar systems, accelerating spacecraft to relativistic speeds with laser arrays or manufacturing antimatter fuel in industrial quantities. They might not even need ships in the traditional sense, just transmit their minds via light pulses or launch microscopic probes that grow into colonies at their destination. And if such structures already exist elsewhere, they'd be cosmic lighthouses, broadcasting the presence of intelligence far louder than any radio signal. Yet the paradox of Dyson spheres is this: the very scale that makes them powerful also makes them invisible. A completed swarm might render its star nearly undetectable in visible light, hiding in plain sight as a cold, dark anomaly. That raises a haunting thought. Could our galaxy be dotted with these shadowed stars, their builders long since moved on to other realms? Or worse, are we simply too primitive to recognize the signs? Whether Dyson Spheres are humanity's future or another civilization's ancient legacy, they force us to confront the cosmic scale of ambition. To reach the stars, we might need to think not in terms of rockets, but in terms of rearranging the heavens themselves, turning suns into engines and light into destiny. Some of the most unsettling footprints in the cosmos might not be left by living beings at all, but by their robotic scouts. The von Neumann probe, named after mathematician John von Neumann, is a hypothetical self-replicating machine designed to spread across the galaxy like a cosmic wildfire. Imagine a single probe landing on a distant asteroid, mining its raw materials to build copies of itself, then launching those copies toward new star systems. Each new arrival repeats the process, creating an exponentially growing network of explorers. Within a few million years, a blink in cosmic terms, these machines could blanket the entire Milky Way, turning every resource-rich world into a factory for more probes. The math behind this is chillingly elegant. Even if each probe took 1,000 years to replicate just once, starting from a single unit, the swarm would number in the trillions within 30,000 years. At that scale, Earth should have been visited countless times already, which leads to one of the most provocative questions in astrobiology: where are they? If self-replicating probes are possible, and if any civilization predating us by even a modest margin built them, our solar system ought to be teeming with their artifacts. Some researchers suggest we might be looking at the evidence all wrong. Perhaps ancient legends of sky gods or strange celestial phenomena are remnants of past visits. Others argue the probes could be microscopic, hidden in plain sight, or even disguised as natural objects. Then there's Bracewell's twist on the idea, the notion that these probes might not just observe but communicate. A network of autonomous sentinels could act as interstellar answering machines, lying dormant until they detect signs of intelligence, then activating to initiate contact. That raises an eerie possibility. If such a probe exists in our solar system, it might have been silently waiting since before humans walked upright, only now beginning to stir as our radio signals ripple outward. The ethical dilemmas are just as staggering as the engineering. A single misprogrammed von Neumann probe could become a galactic plague, converting planets into dead factories without restraint. Sci-fi calls this the grey goo scenario, but the real danger is more clinical, a wave of replication with no off switch consuming everything in its path. To prevent this, theorists suggest strict limits, like probes designed to shut down after a set number of copies or systems that require external authorization to replicate. But therein lies the paradox. The same safeguards that prevent disaster could also render the whole project pointless. A probe that can't adapt might fail when faced with the unexpected chaos of real star systems. Yet the most haunting aspect isn't the technology, it's the timeline. If even one civilization in our galaxy's 13-billion-year history mastered self-replicating probes, their legacy should be everywhere. That we don't see obvious evidence might mean we're alone, or it could mean we're not searching for the right signs. After all, an advanced probe wouldn't announce itself with blinking lights. It might camouflage as space debris, hibernate in deep orbits, or even disguise itself as part of Earth's own tech. So while we dream of sending our own probes to the stars, we might also ask, have we already been harvested? Is some fragment of an ancient machine floating in the Kuiper belt right now, watching, waiting, or worse, replicating? The universe keeps its secrets well, but the longer we search without finding von Neumann probes, the more the silence feels like a riddle we're not yet smart enough to solve. Quantum entanglement might just be the strangest loophole in the universe, a phenomenon so bizarre even Einstein called it spooky action at a distance. Here's how it works. When two particles become entangled, they share a bond that defies space and time. Change the state of one, and the other instantly mirrors that change, no matter how far apart they are. No signal travels between them, no delay, just instantaneous, silent synchronization across light years. If we could harness this for communication, the implications for interstellar travel would be revolutionary. Imagine a starship light years from Earth sending messages back home, not at the speed of light, but instantly. The catch, quantum entanglement doesn't actually transmit information in the way we'd need for traditional communication. Here's the paradox: while the entangled particles react in unison, we can't control the specific state they'll collapse into when measured. It's like having two identical, shuffled decks of cards in separate galaxies. When you draw the Queen of Hearts from one, the other deck's corresponding card will also be the Queen of Hearts, but you didn't choose that outcome. This randomness makes sending deliberate messages like coordinates or warnings impossible under current understanding, yet some theorists refuse to abandon the dream. What if we're missing a piece of the puzzle? Advanced civilizations might have discovered ways to encode information in entangled systems using quantum loopholes we haven't even imagined. Experiments in quantum teleportation, where a particle's state is transferred across distance, hint that controlled transmission might one day be possible. Pair this with quantum computing, and suddenly the idea of an interstellar internet doesn't seem so far-fetched. A ship could deploy entangled particles upon departure, creating a real-time link back to Earth. Even if the voyage takes centuries, the crew could send updates that reach mission control without delay. The darker possibility: someone might already be using this. Unexplained quantum anomalies in deep space observations, like particles behaving as if they're being measured by unseen observers, have fueled speculation that entanglement networks could be operating right under our noses. Ancient texts describing oracles or seers receiving instant knowledge from the gods take on an eerie new light when viewed through this lens. Of course, skeptics argue that entanglement's randomness is fundamental, not a barrier to be overcome. But if there's one lesson from quantum physics, it's this: the universe loves to defy expectations. Whether future humans or something else crack the code, quantum entanglement remains one of the most tantalizing keys to unlocking the stars. And that's what makes it so thrilling. The line between impossibility and breakthrough might just be a single, brilliant insight away. Black holes aren't just cosmic vacuum cleaners, they might be the ultimate slingshot for interstellar travel. Picture a spacecraft skimming just outside the event horizon of a supermassive black hole, riding its gravitational whirlpool like a surfer catching a wave. The physics is sound. A black hole's immense gravity could accelerate an object to a significant fraction of light speed without burning a drop of fuel. This isn't science fiction, it's orbital mechanics on steroids, a technique called the Penrose process after physicist Roger Penrose, who first theorized it in 1969. But here's where things get dicey. The closer you get to a black hole's event horizon, the more extreme the tidal forces become. Imagine your ship being stretched like taffy, your feet pulled harder than your head until atoms themselves start to unravel. Even a supermassive black hole with its gentler gradient would demand precision navigation down to the meter. One wrong calculation, and your ship becomes another silent ripple in the black hole's shadow. Then there's the problem of escape. Unlike a planetary slingshot where you can adjust your trajectory with thrusters, a black hole's grip doesn't let go easily. You'd need enough speed to avoid falling in, but not so much that you're flung into the void without a way home. The energy payoff, though, could rewrite the rules of space travel. Simulations suggest a properly executed black hole slingshot might convert up to 20% of an object's mass into kinetic energy, far more efficient than any rocket. Some theorists even speculate about Kerr black holes, rotating monsters where the Penrose process could extract energy directly from the hole's spin. It's like stealing a fraction of a star's power to fuel your voyage, Yet the biggest hurdle isn't physics, it's geography. The nearest known black hole, Gaia BH1, is over 1,500 light-years away. By the time we reached it with current propulsion, the crew's descendants might have forgotten why they left, unless we discover a closer black hole or someone builds one artificially. This method remains a spectacular but impractical idea. And that raises a chilling thought. Could an advanced civilization have already engineered micro-black holes as propulsion aids? Some interpretations of quantum physics suggest tiny, primordial black holes might exist, relics from the Big Bang. If harnessed, they could serve as portable gravity wells, turning every starship into its own slingshot. We've never detected such objects, but their potential whispers through the equations. Black hole slingshots force us to confront a paradox. The universe's most destructive forces might also be its greatest engines. Whether humanity ever dares to ride that razor's edge between annihilation and acceleration, one thing's clear: the cosmos doesn't offer free lunches. Every shortcut comes with a price, and in the case of black holes, that price is paid in gravitational chaos. What if the speed of light isn't the universe's speed limit, just a hurdle we haven't learned to bend around? Enter the Alcubierre warp drive, a concept so audacious it treats spacetime like a stretchy fabric, crumpling the cosmos ahead of a spacecraft while smoothing it out behind. Proposed by physicist Miguel Alcubierre in 1994, this hypothetical engine wouldn't propel a ship through space faster than light. Instead, it would manipulate the very fabric of reality, creating a bubble of warped spacetime that carries the vessel along like a surfer riding a wave. The result: travel from Earth to Alpha Centauri in weeks or even days without ever breaking Einstein's cosmic speed limit. The mechanics are as elegant as they are bizarre. Imagine spacetime as a rubber sheet. Normally, moving across it requires pushing against it, burning fuel, fighting inertia. But the Alcubierre drive sidesteps all that. By contracting spacetime in front of the ship and expanding it behind, the bubble inside remains undisturbed, floating along while the universe itself does the heavy lifting. Passengers wouldn't feel acceleration or crushing G-forces. They'd simply watch the stars ahead blue shift into oblivion as those behind red shift into darkness. It's the ultimate cosmic loophole, exploiting relativity's fine print to go slow locally while moving impossibly fast globally. But here's the rub: making this work requires something called exotic matter, a theoretical substance with negative energy density. Unlike normal matter, which gravity attracts, exotic matter would repel, acting as the scaffolding to bend spacetime into the necessary warp bubble. The problem: we've never observed such material in nature. Quantum physics hints that negative energy might exist in microscopic amounts. Think the fleeting quantum foam of empty space, but scaling that up to warp drive levels would demand more energy than exists in entire galaxies. Some calculations suggest the initial energy requirement equals converting Jupiter's entire mass into pure energy. Not exactly practical for a Tuesday afternoon test flight. Yet the dream isn't dead. Recent refinements to Alcubierre's math suggest a slimmer warp bubble could reduce energy needs dramatically from planetary scales down to something akin to a small moon. Other theorists propose harnessing the mysterious dark energy accelerating the universe's expansion, though we're no closer to understanding how. And then there's the unsettling possibility that advanced civilizations might have already cracked it. Unexplained astrophysical anomalies like cosmic rays with no clear source or fleeting distortions in distant starlight have fueled speculation that we're witnessing the wake of someone else's warp experiments. The greatest hurdle might not be physics but paradox. Warp drives flirt dangerously with time travel thanks to relativity's tangled rules. A ship arriving before its own light could theoretically send messages backward in time, creating causality loops where effects precede causes. Navigating that minefield would require rewriting our understanding of reality itself. or accepting that the universe allows for timelines messier than any sci-fi plot. So is the Alcubierre drive just a beautiful mirage for now, yes, but it represents something profound: humanity's refusal to accept impossible as anything more than a temporary roadblock. Every flight once seemed magical, every ocean too vast to cross. The warp drive might forever remain a quirk of equations, or it might be the blueprint for our future among the stars, waiting for the day we learn to fold the heavens like paper. Until then, it stands as a reminder that the universe's rules are stranger and softer than they appear. What if the first interstellar travelers didn't vanish into the depths of space but slipped sideways into realities we can't perceive? The idea of parallel universe jumping turns the mystery of Fermi's paradox on its head. Perhaps we haven't found traces of ancient starfarers because they're not just elsewhere in our universe, but in other universes entirely. This isn't just wild speculation, it's a fringe but tantalizing possibility rooted in theories like the multiverse and quantum branching, where every decision, every random event spawns new timelines. Imagine a civilization that didn't just master space travel, but reality hopping, bending the fabric of existence to step between worlds like doors in an endless corridor. The math behind this is as mind-bending as the concept. Some interpretations of string theory suggest our universe might be one of countless brains, short for membranes, floating in a higher dimensional space, occasionally brushing against others. If a society discovered how to puncture the barrier between these brains, they could effectively shortcut across cosmic distances by moving through dimensions beyond our perception. Think of it like this: instead of sailing across an ocean, they found a hidden tunnel beneath it, one that leads not just to another shore, but to an entirely different ocean. The technologies involved would dwarf anything we've imagined, from harnessing energies at the Planck scale to manipulating the very substrate of spacetime. But here's the chilling twist: if travelers did cross into parallel universes, their absence in ours wouldn't be a mystery, it'd be inevitable. Ancient myths might hold clues. Stories of vanishing cities, gods stepping between realms, or entire civilizations swallowed by the Earth could be garbled accounts of interdimensional leaps. Even modern UFO sightings often describe craft that don't just move erratically, but seem to blink in and out of existence as if flickering between realities. Could these be glimpses of travelers from or to another branch of the multiverse? The implications spiral outward. A multiverse-hopping civilization wouldn't just leave no physical traces, their very existence might be undetectable by conventional means. Radio signals, they'd broadcast on frequencies tuned to their home reality's physics. Artifacts, perhaps their materials decay instantly in our universe's slightly different quantum rules. Even their biology might be incompatible with our version of reality, like a fish trying to breathe in a desert. This could explain why the cosmos seems so silent. We're not listening for the right kind of noise. Yet the most unsettling possibility isn't that they're gone, but that they're still here, just out of phase. Some theoretical models suggest parallel universes could overlap like ghostly echoes, occasionally interacting in ways we can't predict. A starship might hover right beside us, separated by a veil thinner than an atom, forever unseen. Or worse, what if their experiments in universe jumping triggered catastrophic collapses in neighboring realities, leaving them stranded or annihilated? The darkest solution to Fermi's paradox might be that someone opened a door they couldn't close, and the silence we hear is the echo of their demise. Of course, skeptics dismiss this as unfalsifiable fantasy. Without observable evidence, parallel universe travel remains in the realm of metaphysics. But the sheer scale of cosmic mystery demands we consider every angle, even the ones that twist through dimensions we can't yet fathom. Whether a cautionary tale or a blueprint for humanity's next leap, the idea forces us to ask, if the stars are lonely, maybe we're just looking in the wrong direction. The greatest voyages might not be through space, but through the infinite layers of reality itself. Imagine trillions of microscopic spacecraft, each no larger than a grain of sand, launching toward the stars not as lone explorers but as a coordinated swarm, a celestial hive mind. This is the promise of nanotechnology-driven interstellar travel, where size and speed trade places with numbers and patience. Instead of sending one fragile ship across the void, this approach floods the cosmos with tiny, self-sufficient probes, each carrying the blueprint for something greater. Upon arrival, they could assemble like cosmic Lego bricks into telescopes, research stations, or even habitats, transforming a distant star system without a single human ever making the journey. The scale of this vision defies intuition. Picture a cloud of nanobots so vast it could blanket a city, yet so lightweight that a single rocket launch could carry quadrillions of them. Unlike traditional spacecraft burdened by fuel, life support, or radiation shielding, these probes would rely on redundancy. If 99% fail en route, the surviving 1% still amounts to billions of units. Some designs propose sails thinner than atoms, pushed by lasers to relativistic speeds. Others suggest hibernation modes where bots shut down for centuries, only awakening when sensors detect their target star's light. Their power wouldn't come from bulky reactors, but from microscopic solar panels or even ambient starlight harvested molecule by molecule. But the real magic lies in what happens after the swarm arrives. Inspired by biological systems like ant colonies or beehives, these nanobots could communicate through localized networks, sharing data and tasks without centralized control. One group might mine asteroids for raw materials, while another uses those resources to 3D print larger structures. Over decades, a symphony of tiny machines could erect a megastructure visible across light years, all without human intervention. This isn't just exploration, it's cosmic terraforming by way of a trillion tiny hands. The challenges, however, loom as large as the possibilities. Interstellar dust becomes deadly at high speeds. A single particle could vaporize a nanobot. Radiation might fry delicate circuits over centuries. And then there's the puzzle of coordination. How do you program AI simple enough to fit on a spec-sized chip, yet sophisticated enough to improvise around unknowns? Some theorists propose evolutionary algorithms where bots adapt through trial and error, mimicking natural selection. Others suggest pre-programming them with libraries of possible scenarios, like chess players anticipating moves in a game lasting millennia. Perhaps the most haunting question isn't technical but philosophical. If a swarm can build, learn, and adapt, does it count as a traveler or something more? Ancient myths speak of self-replicating clay golems or mechanical angels. Are these early intuitions of a future where humanity's ambassadors to the stars aren't flesh and blood, but something stranger? And if another civilization beat us to this idea, their probes might already be floating in our oceans, hiding in our soil, or passing through our atmosphere, too small to notice, too numerous to stop. The beauty of the swarm approach lies in its humility. Instead of betting everything on a single ship, it embraces the universe's vastness with equal vastness. It's not about conquering space, but saturating it, turning the cosmos into a canvas where every atom might one day hum with purpose. Whether this is how humanity takes its first interstellar step, or how something else already did, remains to be seen. But the lesson is clear. Sometimes the future isn't built with giant leaps, but with billions of tiny, patient steps. The universe might be threaded with invisible superhighways left over from its birth cosmic strings, defects in the fabric of spacetime so dense, a single inch could weigh more than Mount Everest. These hypothetical relics of the Big Bang aren't just scientific curiosities. They could be the ultimate shortcut for interstellar travel. Picture a string stretching across light years, its immense gravity warping spacetime around it like a taut wire pressing into foam. A ship skimming along this cosmic tightrope could, in theory, ride its gravitational distortion to reach distant stars in a fraction of the time it would take through conventional space. The math behind this is as elegant as it is mind-bending. Cosmic strings, if they exist, would be unimaginably thin, no wider than a proton. Yet their density would create a gravitational field so intense, spacetime itself would curve into a sort of natural warp corridor. Move parallel to the string and you'd experience minimal resistance. Approach it at the right angle, and its gravity could slingshot you forward at velocities approaching light speed without the need for fuel. It's like finding a cosmic conveyor belt hidden in the void, one laid down in the universe's first moments and left untouched for billions of years. But finding these strings is another matter entirely. Unlike black holes or neutron stars, cosmic strings wouldn't emit light or radiation. Their presence would only betray itself through subtle distortions, light from distant galaxies bending around nothing, twin images of the same star split by an invisible lens, or ripples in the cosmic microwave background. Some researchers have scoured sky surveys for these anomalies, and a handful of candidates have emerged, though none confirmed. The irony is thick. The ultimate interstellar highway might be lurking in plain sight, visible only through its ghostly fingerprints. Even if we found one, harnessing it would demand technology bordering on the miraculous. The gravitational forces near a cosmic string could tear matter apart atom by atom, requiring shields far beyond anything we've dreamed up. Navigation would be a nightmare. Veer too close and your ship gets spaghettified. Drift too far and the effect vanishes. And then there's the existential risk. Some models suggest cosmic strings could be unstable, snapping like over-tensioned rubber bands with enough energy to obliterate solar systems. Not exactly the kind of pothole you'd want to hit mid-journey, yet the allure is impossible to ignore. If even one string exists within reach, it could transform the galaxy from an impassable gulf into a navigable network. Ancient cultures spoke of celestial bridges or roads walked by gods. Could these myths be dim memories of a time when someone else found and used these threads? The idea isn't entirely far-fetched. A sufficiently advanced civilization might treat cosmic strings like interstellar railroads, building infrastructure around them the way we cluster cities along rivers. The most haunting possibility: we might be late to the party. If strings are as rare as current theories suggest, the first species to map them could monopolize the cosmos's fastest routes, leaving everyone else stuck in the slow lanes of ordinary space. That could explain why the universe feels so empty, not because life is rare, but because the quickest paths were claimed eons ago, their owners now watching from the cosmic equivalent of gated communities. Cosmic strings force us to confront a thrilling, if unsettling, truth. The universe might be full of hidden tools, leftovers from its creation waiting to be repurposed. Whether they're the key to our interstellar future or relics of someone else's past, they remind us that the cosmos is stranger and richer than our unaided eyes can see. The highways are out there, if only we can learn to read the map. Imagine a starship that doesn't just carry life, it is alive. A vast, breathing organism grown from genetically engineered cells, its hull not metal but thickened hide, its engines not combustion chambers but pulsing muscle tissue. This is the vision of biological spacecraft, where technology and biology blur into something entirely new. While traditional ships rely on brittle circuits and finite fuel, living vessels could heal themselves, adapt to cosmic radiation, even grow fresh supplies from onboard ecosystems. The concept isn't pure fantasy. Nature already thrives in the harshest environments, from bacteria surviving in nuclear reactors to tardigrades enduring the vacuum of space. What if we could harness that resilience and scale it to the size of a starship? The advantages are tantalizing. A biological ship could repair micrometeorite damage the way skin heals a scrape, filter cosmic rays through specialized membranes, or photosynthesize energy from starlight like deep-sea vent organisms harnessing geothermal heat. Waste recycling wouldn't require complex machinery, just symbiotic bacteria breaking down materials into nutrients. Crews might even cultivate farm zones aboard the ship, where genetically modified plants or fungi produce oxygen, food, and medicine in closed loops. And unlike metal hulls that degrade over centuries, living structures could regenerate indefinitely, given the right conditions. For generation ships or long-duration voyages, this could mean the difference between arriving at a new star system with a crumbling wreck or a thriving, evolved organism stronger than when it launched. But biology is messy. Living systems are unpredictable, prone to mutations or diseases no engineer can fully anticipate. A fungal infection in the ship's nutrient veins or a cancer-like overgrowth in its neural network could spell disaster. Then there's the ethical weight of creating sentient vessels. Would a ship capable of self-repair also feel pain? Ancient mariners spoke of ships having souls. In this scenario, that might be literal. Some theorists propose hybrid designs where biological components handle regeneration and life support while traditional tech manages navigation. Others envision fully organic ships grown from synthetic DNA, their brains decentralized like octopus neurons with no consciousness but unparalleled adaptability. The most radical idea that we're not the first to try this. UFO accounts often describe craft with smooth, almost fleshy surfaces, or that change shape like living tissue. Could these be relics of a civilization that mastered bioengineering long before we invented the microchip? Even Earth's mythology brims with organic vessels, Noah's Ark as a floating ecosystem, or Greek tales of the Argo, whose prow was carved from a magical speaking oak. These stories might be metaphors or distant echoes of a forgotten technology. The truth is, biology already solved interstellar travel once, just not the way we'd prefer. Panspermia, the theory that life hops between planets on asteroids, proves organic material can endure millennia in deep space. A biological ship would simply be taking nature's blueprint and scaling it up with intention. Whether this path is humanity's future or a cautionary tale waiting to unfold, one thing's certain: the line between spacecraft and lifeform has never felt so thin. And somewhere in that ambiguity lies a truth we're only beginning to grasp: that the universe might not favor machines, but something far stranger, something alive. Dark matter is the universe's most enduring enigma, invisible, untouchable, yet outweighing all visible matter 5-1. What if this ghostly substance, currently detectable only by its gravitational whisper, could be the key to unlocking the stars? The idea of dark matter propulsion pushes the boundaries of physics into uncharted territory, suggesting that the very stuff we can't see or hold might become the ultimate fuel for interstellar travel. Unlike conventional rocket fuel, which relies on explosive chemical reactions or the controlled fury of nuclear fusion, dark matter would exploit a far subtler phenomenon: its gravitational influence. Since dark matter doesn't interact with light or ordinary matter except through gravity, harnessing it would require technologies beyond anything we've built. Picture a spacecraft equipped with a dark matter scoop, a theoretical device that could somehow gather and concentrate these elusive particles as the ship moves through space. As dark matter accumulates, its collective gravity could be used to warp spacetime around the vessel, creating a localized distortion that propels the ship forward without traditional thrust. It's like sailing on the cosmic wind, only the wind is made of shadows. The challenges, of course, are monumental. We don't even know what dark matter is made of, let alone how to capture or manipulate it. Current detectors buried deep underground, like the LUX Zeppelin experiment, hunt for the rare occasions when a dark matter particle might bump into an atomic nucleus. Even then, these interactions are so feeble they're almost impossible to measure. Scaling that up to a propulsion system would mean finding a way to attract dark matter in vast quantities, assuming it can even be contained. Some models suggest that certain types of dark matter, like hypothetical weakly interacting massive particles WIMP, might annihilate upon contact with each other, releasing energy. If true, a ship could theoretically burn dark matter as fuel, converting it into usable thrust. But without proof these particles exist, the idea remains a dazzling mirage. Yet the potential is too extraordinary to ignore. Dark matter is everywhere, permeating galaxies in vast halos. A vessel that could tap into this invisible reservoir would never run out of fuel, needing only to pass through dense clouds of dark matter to refuel. Unlike antimatter or fusion, which require massive infrastructure to produce, dark matter is already there, waiting. Some theorists even speculate that advanced civilizations might have already cracked this puzzle, using dark matter highways to navigate the cosmos undetected. After all, if your engines leave no heat signature, no light trail, how would anyone know you were there? The most tantalizing aspect isn't just propulsion, it's stealth. A dark matter-powered ship wouldn't glow against the blackness of space. It wouldn't spew radiation or leave exhaust plumes. To outside observers, it might be as invisible as dark matter itself. That raises a spine-tingling possibility. Could unidentified aerial phenomena on Earth be glimpses of such technology? Brief distortions in gravity fields, objects moving with no visible means of propulsion. These are the hallmarks of a craft that bends the rules of physics as we know them. Of course, skeptics argue that dark matter's very nature makes it useless for engineering. If it doesn't interact with normal matter except through gravity, how could we ever build a device to collect or direct it? But history is littered with breakthroughs once deemed impossible. The Wright brothers flew just 66 years after physicists declared heavier-than-air flight unachievable. Dark matter propulsion might be a pipe dream today, but so was splitting the atom in 1900. Whether this theory ever moves beyond speculation, it forces us to confront a humbling truth. The universe is brimming with resources we're only beginning to perceive. The greatest engine for interstellar travel might not be something we invent, but something we've yet to truly see. And that's the thrill of the unknown. The next leap could be hiding in plain sight, woven into the invisible fabric of the cosmos itself. What if the stars we yearn to reach aren't distant points of light, but pixels in a cosmic simulation, waiting to be rewritten? The holographic principle, a mind-bending idea born from quantum physics and black hole thermodynamics, suggests that our three-dimensional universe might be a projection of information encoded on a two-dimensional surface at its edge. Think of it like a movie theater screen. The images appear deep and real, but they're ultimately flat data playing tricks on our senses. If this theory holds, interstellar travel could transcend rockets and warp drives entirely. Instead of crossing vast distances, we might one day learn to edit the code of reality itself, teleporting between stars by rearranging the universe's fundamental bits like a programmer debugging a cosmic simulation. The math behind this isn't science fiction, it's rooted in the study of black holes. When matter falls into a black hole, the information it carries doesn't vanish. It's scrambled and smeared across the event horizon like a scrambled hard drive. This observation led physicists like Leonard Susskind and Gerard T. Hooft to propose that all the information inside a volume of space, every star, planet, or human thought, could be encoded on its boundary. In other words, the universe might operate like a hologram, where what we perceive as depth is actually information painted on a flat surface we can't see. If true, this would mean that every journey we've ever taken, from walking to the store to flying to the moon, is just data being recalculated in real time on a cosmic hard drive. Now imagine applying that to interstellar travel. Instead of building ships to plod across light years, a civilization that cracked the holographic code could manipulate the underlying rules of the simulation. Need to reach Alpha Centauri? Rewrite your coordinates in the universe's source code. Hit an asteroid, roll back the program like reloading a saved game. The implications are staggering. Distance becomes irrelevant when you're not moving through space, but editing it. Some theorists even suggest that unexplained quantum phenomena, like particles teleporting through barriers or instantly influencing each other across light years, might be glitches in the system, hints that reality is more malleable than it seems. But here's where the theory gets eerie. If the universe is a hologram, who's running the simulation? Are we the accidental creations of some higher dimensional programmers? Ancient myths from the Vedas to Gnostic Christianity speak of worlds being illusions or dreams of gods. Could these be primitive intuitions of the holographic truth? Even modern UFO accounts often describe craft that materialize out of thin air or vanish without a trace, as if someone toggled their visibility settings. The most unsettling possibility isn't that we're alone in the universe, it's that we're characters in a cosmic game, and the developers never intended us to access the debug menu. Skeptics, of course, dismiss this as metaphysical fantasy. Without empirical proof, the holographic principle remains a tantalizing what if. But the irony is thick. If we're living in a simulation, any evidence we find could just be part of the program. Still, the idea forces us to confront a profound question. Is reality a fixed stage we must painfully cross, or a dynamic construct waiting to be remade? Whether the holographic universe is humanity's future or just a beautiful dead end, one thing's certain: it turns the night sky into something far stranger than a map of destinations. It becomes a screen flickering with possibilities, and we're just beginning to guess the password. The idea that our first interstellar visitors might not come from distant stars, but from distant futures, turns the search for alien life on its head. What if the mysterious travelers we've been waiting for aren't extraterrestrials at all, but our own descendants, equipped with technology that lets them slip backward through time as effortlessly as we board airplanes? This twist on the Fermi paradox suggests that the universe feels empty not because civilizations die out, but because they master time travel first, visiting the past as tourists rather than colonizing the present. Time travel might sound like pure fantasy, but the physics isn't as dismissive as you'd think. Einstein's relativity allows for closed time-like curves, loops in spacetime where the future circles back to meet the past. Under extreme conditions, like the intense gravity near a rotating black hole or cosmic strings, these loops could theoretically form. A civilization advanced enough to manipulate space-time might not just hop between stars, they might hop between centuries, treating history like a sightseeing itinerary. The eerie part: if they've already perfected it, we'd never know. A time tourist from the year 5000 could be standing beside you right now, their presence hidden by technology that renders them invisible, or so mundane-looking we'd never glance twice. And that raises a chilling possibility. Perhaps we've already encountered them. Historical records brim with accounts of out-of-place artifacts, like the Antikythera mechanism, a 2,000-year-old device resembling a mechanical computer, or the Dorchester pot, a metallic vase allegedly found embedded in solid rock dating back millions of years. Even modern UFO sightings often describe craft that appear and vanish instantaneously, move without inertia, or change shape in ways that defy physics as we know it. Could these be not alien visitors, but human ones, time travelers conducting archaeological expeditions to their own species' past? The ethical dilemmas are just as mind-bending as the physics. Would future historians have rules against interfering with their own timeline, like a starfaring prime directive? Some theorists argue that any civilization capable of time travel would inevitably splinter into factions, some trying to preserve history, others trying to rewrite it. The wars of the future might not be fought over territory, but over causality itself. This could explain why we haven't been contacted openly. The winners of those conflicts enforce strict non-interference to prevent paradoxes that unravel their existence. Then there's the darker alternative. What if time travel is a one-way trip to the past? Energy requirements might make returning to one's original era impossible, stranding travelers in bygone centuries with no way home. That could mean any historical mystery, from the construction of the pyramids to the sudden disappearance of advanced cultures like the Maya, might be the work of marooned time tourists, using their residual knowledge to influence the past before fading into obscurity. The most tantalizing clue might be hiding in plain sight: our own obsession with time travel. Every culture has myths of prophets, oracles, or seers glimpsing the future. Modern science fiction is saturated with tales of chronological jumps, from H.G. Wells' Victorian time machine to blockbuster films. Could this collective fascination be more than imagination, a subconscious pull toward a technology our descendants have already mastered? Whether time-traveling explorers are out there, or rather, out when remains one of the universe's great unanswerables, but it forces us to reconsider what first contact might look like. The strangers knocking at our door may not come from the stars, but from the calendar pages we haven't yet turned. And that changes everything, because the future isn't just a destination. It might already be watching. Solar sails and antimatter seem like opposites, one harnessing the gentle push of photons, the other unleashing the most violent energy release known to physics. But what if combining these extremes creates the ultimate interstellar engine? Picture a spacecraft with vast, gossamer sails, not just catching sunlight, but riding the annihilation shockwaves of antimatter explosions. This hybrid approach could solve the Achilles heel of both technologies. Light sails struggle to reach blistering speeds, and antimatter's catastrophic hunger for fuel. The mechanics are as brilliant as they are brutal. A traditional light sail relies on photons, particles of light bouncing off its surface, each imparting a minuscule push. Over years, this constant pressure can accelerate a probe to notable fractions of light speed. But antimatter changes the equation entirely. When a single gram of antimatter meets normal matter, it converts entirely into energy with 100% efficiency, releasing the equivalent of a 20-kiloton nuclear bomb. Now imagine channeling that fury. Instead of relying solely on sunlight, a hybrid sail could deploy microscopic antimatter pellets at precise intervals behind it. Each pellet's annihilation would produce a directed blast of gamma rays and high-energy particles, striking the sail like a cosmic hammer, delivering kicks of acceleration far beyond what sunlight alone could provide. Breakthroughs in antimatter containment make this less fantastical than it sounds. Recent experiments at CERN have trapped antimatter atoms for over 17 minutes using magnetic fields. A blink compared to interstellar mission durations, but proof that control is possible. For a solar antimatter hybrid, you wouldn't need to store vast quantities. A few nanograms of antimatter, released in timed pulses, could provide the bursts needed to push past the speed ceilings of conventional light sails. Some designs propose dusty plasma sails lined with materials that convert gamma rays into additional thrust, turning the antimatter's destructive output into controlled propulsion. The real magic lies in the numbers. A pure light sail heading to Alpha Centauri might take decades to reach 20% light speed. Add antimatter boosts, and that timeline could shrink to a decade or less. That's fast enough for a robotic mission to return data within a human lifetime, or even for a heavily shielded crewed vessel to make the trip without confronting the soul-crushing spans of generation ships. And unlike antimatter rockets, which require staggering fuel quantities to offset their own mass, the hybrid approach uses antimatter sparingly as a booster rather than the primary engine. But the challenges loom as large as the potential. Antimatter production remains agonizingly slow. Current facilities generate about 1/1,000,000th of a gram per year at costs exceeding $60 billion per gram. Then there's the sail itself. It would need to withstand not just the gentle pressure of sunlight, but the hammer blows of antimatter explosions without vaporizing. Advanced materials like atomically thin graphene or metamaterials that disperse energy might offer solutions, but they're still in their infancy. and the timing must be flawless. Mistimed antimatter bursts could shred the sail or send the probe tumbling off course with no way to recover. The most haunting question isn't technical, it's existential. If this hybrid propulsion is feasible, why haven't we detected signs of it elsewhere? Gamma-ray bursts from antimatter annihilation would leave distinct signatures across interstellar distances. Yet the cosmos seems silent. That absence could mean we're pioneering something unprecedented, or that there's a catastrophic flaw we've yet to uncover. Alternatively, perhaps advanced civilizations use stealthier methods, like masking their bursts behind natural phenomena or switching to entirely different technologies once they master antimatter's secrets. There's a poetic symmetry to this marriage of extremes. Light sails embody patience, a whisper of momentum accumulated over years. Antimatter is all violence, a scream of energy over microseconds. Together, they might be the key to crossing the interstellar void without sacrificing speed or sanity. Whether this hybrid remains a tantalizing theory or becomes humanity's ticket to the stars depends on solving riddles that straddle the line between engineering and alchemy. But one thing's certain, in the quest to reach other suns, the most powerful solutions might come from embracing contradictions. Imagine stepping into a scanner, closing your eyes, and waking up instantly on a planet orbiting Alpha Centauri, not as a human, but as pure consciousness beamed across space at the speed of light. This isn't just a futuristic daydream, it's the radical premise of interstellar travel without ships, where the body stays behind and the mind becomes the explorer. The concept hinges on two jaw-dropping possibilities: that human consciousness can be digitized like software, and that this data could be transmitted through the cosmos as effortlessly as radio waves carry music. If true, it would turn the universe into a vast digital playground, where travel means uploading your thoughts to a receiver on the other side of the galaxy. The foundation of this idea rests on advancements in neuroscience and computing that are already blurring the line between mind and machine. Brain-computer interfaces like Neuralink are proving we can translate neural activity into digital signals, while projects like the Blue Brain Initiative aim to recreate human consciousness inside supercomputers. The leap from mapping synapses to fully uploading a mind is staggering but not implausible. Some theorists suggest that within a century, we might crack the neural code, allowing personalities, memories, and even senses to exist as transferable data. The implications rewrite every rule of space exploration. No more life support systems, no generational ships, just consciousness zipping between stars as encoded light. But the real magic lies in the transmission. A digitized mind could be beamed via lasers or radio waves, traveling at light speed without the constraints of physical mass. This galactic internet would require relay stations, perhaps autonomous probes or alien-built nodes, to catch and redirect signals across interstellar distances. Like cosmic Wi-Fi routers, these stations could form a network spanning the Milky Way, allowing minds to hop from node to node like packets of data. The time lag would still exist. Alpha Centauri's 4-year transmission delay means you'd arrive 4 years after sending, but for an uploaded consciousness, those years could feel like the blink of an eye. Time dilation and aging become irrelevant when your data in transit. Ethical quicksand surrounds this vision. Is the transmitted you still you, or just a copy with your memories? Philosophers call this the teletransportation paradox, and it's more than semantics. If your earth-bound body remains while your digitized self wakes up light years away, which one holds your identity? Some argue that consciousness is inherently continuous, that the copy would be a new entity, leaving the original you trapped in mortal flesh. Others propose gradual uploading, replacing brain tissue with synthetic components piece by piece until nothing biological remains. It's the ship of Theseus rewritten for the space age. Then there's the eerie question of who else might be using this network. If transmitting minds is possible, advanced civilizations could have been doing it for millennia. The cosmos might be teeming with digital beings, former biological entities who traded flesh for the freedom of light-speed existence. These post-biological intelligences could be invisible to traditional searchers for alien life, since they'd leave no physical traces. SETI radio telescopes might be listening for the wrong thing entirely. The real aliens could be streams of data flowing between stars, their conversations embedded in cosmic background noise. Practical hurdles abound, protecting transmitted minds from cosmic interference like gamma rays scrambling the signal would require error correction beyond anything we've invented. And what awaits at the destination? A robotic body, a virtual world, a lab-grown biological host. The darkest scenario is finding receiver stations already occupied by entities that repurpose uploaded minds for their own ends. Ancient astronaut theories take on a new twist. What if abductions are just unauthorized downloads, yet the allure is undeniable? For species facing the brutal physics of interstellar travel, digitization offers an elegant workaround, trading fragile bodies for immortal data. Whether this is humanity's inevitable future or a cautionary tale of lost humanity depends on how we view consciousness itself. One thing's certain: if the first interstellar travelers aren't beings at all, but minds riding beams of light, the universe just got stranger and closer than we ever imagined. The vast, silent stretches of our solar system might not be as empty as they seem. Lurking in the shadowed craters of Mars, camouflaged among the icy rocks of the Kuiper Belt, or hidden beneath the sulfurous clouds of Venus, alien outposts could be watching, waiting. The idea that extraterrestrials might have established covert bases in our cosmic backyard isn't just paranoid fantasy. It's a chillingly pragmatic strategy for interstellar travel. After all, why cross the unimaginable gulf between stars in a single marathon sprint when you can hopscotch across planets, using each as a pit stop to refuel, regroup, or observe? Consider Mars, a world that's teased us with anomalies for decades. The infamous face on Mars might have been debunked as a trick of light, but other enigmas persist. Strange, geometrically aligned formations in the regions of Cydonia and Utopia Planitia, transient methane spikes with no clear geological source, and even NASA's own rovers capturing images of unnervingly symmetrical rocks that resemble skeletal fragments or metallic debris. While skeptics dismiss these as pareidolia, our brains imposing patterns on randomness, the sheer volume of oddities raises eyebrows. If an advanced species wanted to monitor Earth without revealing themselves, Mars offers the perfect vantage point, close enough for surveillance, hostile enough to deter prying human eyes. Then there's the asteroid belt, a sprawling junkyard of cosmic rubble that could hide anything. Imagine a stealth base built inside a hollowed-out asteroid, its exterior appearing as just another rock tumbling through space. Inside, advanced tech could harness the asteroid's metals for repairs, its ice for fuel, and its bulk for radiation shielding. This isn't sci-fi speculation. It's a strategy humans have already theorized for our own deep space habitats. Now flip the script. What if someone else got there first? The belt's chaotic orbits would provide natural cover, making artificial structures nearly impossible to distinguish unless they chose to reveal themselves. But the most tantalizing and terrifying candidate might be right next door: Venus. Beneath its crushing, acid-laced atmosphere lies a mysterious, habitable zone, about 50 kilometers above the surface, where temperatures and pressures mirror Earth. While the surface fries at 460 degrees Celsius, this high-altitude layer could, in theory, host floating structures, balloon-like habitats, or even cloud-borne factories refining atmospheric carbon into fuel. Declassified Cold War-era reports from Soviet and American probes describe unexplained flashes and transient geometric shapes in Venus's clouds. Could these be artifacts of something more than lightning? The implications are staggering. If alien bases exist in our solar system, they'd explain the Fermi paradox's eerie silence. Advanced civilizations wouldn't need to broadcast their presence across light years. they'd operate silently from nearby shadows, studying us like biologists observing a petri dish. Ancient astronaut theorists point to myths of gods descending from the heavenly spheres or residing in floating cities as potential echoes of such outposts. Even modern UFO sightings often describe crafts emerging from or retreating toward celestial bodies. Not distant stars, of course. Occam's razor suggests these mysteries likely have mundane explanations: geological quirks, instrumentation errors, or human imagination run wild. But the possibility lingers like a half-heard whisper. If we're not alone in the universe, we might not be alone in our own neighborhood. And that changes everything, because the first contact might not come from the depths of space, but from the rocky wasteland next door, where something has been watching us all along. Artificial black hole drives sound like the fever dream of a mad scientist until you crunch the numbers. These theoretical engines wouldn't just harness gravity like slingshots around cosmic giants. They'd carry their own miniature black holes on board, tapping into the most efficient energy conversion process in the universe: Hawking radiation. Picture a spacecraft fueled by a pinprick of infinite density, a singularity no wider than an atom, yet hotter than a star's core, methodically evaporating to propel humanity between the stars. Here's how the physics dances on the edge of possibility. When black holes lose mass through quantum effects at their event horizons, they emit radiation, a slow leak of energy that, for microscopic black holes, becomes a torrent. A black hole weighing 1,000,000 metric tons would shine with the brightness of 1,000 nuclear power plants, yet fit inside a proton. Contain it in a magnetic bottle, and that energy could be channeled into thrust, either by directing the Hawking radiation as exhaust or using it to heat propellant. The numbers dazzle. 1 gram of matter converted into a micro-black hole could provide more energy than burning 1,000,000 kilograms of rocket fuel. But creating these cosmic power cells is where reality bites back. To forge a black hole artificially, you'd need to compress matter beyond anything our technology can achieve, reaching pressures found only in the hearts of collapsing stars or the first instance after the Big Bang. Some theorists suggest futuristic particle accelerators looping around the moon's circumference might muster the necessary collisions. Others propose tapping into hypothetical cosmic phenomena like quantum foam fluctuations or extra-dimensional physics to tease singularities into existence. The darkest twist: a single miscalculation could birth a black hole that doesn't evaporate quickly enough, sinking through the ship's hull and into the Earth, where it would devour the planet from the inside out. Even if fabrication were solved, containment is its own nightmare. The same magnetic fields used in fusion reactors might corral the black hole's fury, but Hawking radiation isn't gentle. It's a lethal spray of gamma rays and high-energy particles. A spacecraft would need shielding worthy of a star's core or risk cooking its crew in seconds. Then there's the fuel dilemma. Feed the black hole too much and it grows stable, becoming a permanent hazard. Feed it too little and it vanishes before reaching the destination, leaving the ship adrift. Precision would be the difference between propulsion and apocalypse, yet the allure is undeniable. Unlike antimatter, which requires factories the size of cities to produce micrograms, micro-black holes could be manufactured from humble materials. Any matter will do, compressed to its Schwarzschild radius. And their energy-to-mass ratio dwarfs every alternative. Imagine probes reaching relativistic speeds without carrying fuel at all, just nibbling asteroids to feed their hungering cores. Or generation ships powered by singularities that outlast centuries, their black hole hearts glowing faintly like cosmic embers in the dark. The most haunting question isn't whether we could build such an engine, it's whether someone already has. Unexplained gamma-ray flashes in deep space, vanishing stars with no supernova, even the eerie, empty jets detected in some galaxies where black holes should reside. These could be the exhaust trails of civilizations riding singularities we've yet to comprehend. If true, the universe might be crisscrossed with highways built from the corpses of dead stars, their architects long since moved on to stranger horizons. Black hole drives force us to confront a fundamental truth. The universe's most destructive forces might also be its greatest gifts. Harnessing them isn't just engineering, it's alchemy on a cosmic scale, spinning annihilation into motion. Whether this is humanity's future or just another beautiful dead end, one thing's clear: the line between genius and hubris has never been thinner, and somewhere in that balance lies the key to unlocking the stars or becoming their latest cautionary tale. The universe's first moments weren't just a bang, they were a runaway explosion of spacetime itself, stretching the cosmos from smaller than an atom to something astronomically vast in a fraction of a second. This frenzied expansion, known as cosmic inflation, might have done more than shape the universe. It could have flung entire civilizations across galaxies before stars even finished forming. The idea sounds like pure mythology, but buried in the equations of quantum physics lies a staggering possibility. If any intelligent life existed in that primordial chaos, inflation might have scoured them across the cosmos like ink blots on stretching rubber, making them the universe's accidental and first interstellar travelers. Picture this: a hyper-advanced society somehow surviving in the seething quantum foam of the early universe, their existence fleeting as soap bubbles in a storm. Then inflation hits, a force so violent it makes supernova look gentle. In less than a trillionth of a second, space-time stretches by a factor of 10 to the power of 26. That's like expanding a single grain of sand to the size of the observable universe almost instantly. If this civilization clung to a patch of space-time that got caught in the tidal pull of inflation, they wouldn't just be carried to another star, they'd be plastered across light years, their world torn into fractal shreds and scattered like cosmic confetti. Their survival would demand technologies beyond our wildest sci-fi, structures that could reconfigure atom by atom as space itself deformed, or consciousnesses that could fragment and reassemble across expanding dimensions. The echoes of such an event might linger in ways we're only beginning to guess. Some interpretations of the cosmic microwave background, the afterglow of the Big Bang, show anomalous patterns that defy standard physics. Could these be the scars of structures or signals stretched to galactic scales by inflation? Even wilder, what if dark matter, the invisible glue holding galaxies together, isn't a particle at all, but the quantum debris of civilizations shattered and smeared across space-time? The math is as speculative as it is thrilling. Inflation's sheer violence would have redshifted any remnants into near undetectability, like a scream stretched into a whisper over billions of years. But if even a trace survived, it would rewrite not just the history of life in the universe, but the timeline of life itself. The darkest twist: if inflation truly carried ancient travelers, their fate would be worse than extinction. Stretched beyond the cosmological horizon, their fragments would have crossed boundaries where space expands faster than light can travel, cutting them off from the rest of reality forever. No signal could escape, no rescue possible. They'd be the ultimate castaways, imprisoned in isolated pockets of a universe growing colder and emptier by the second. This raises a chilling corollary to Fermi's paradox. The first interstellar travelers might not be missing because they died, but because the cosmos itself exiled them. Yet the most tantalizing question isn't about the past, but the future. If inflation happened once, could it happen again? Some models of multiverse theory suggest pocket universes constantly bud off from ours, each with its own runaway expansion. A civilization mastering the physics of space-time might not just survive inflation, they could trigger it, creating custom universes as cosmic lifeboats or even as experiments. The ultimate interstellar travel wouldn't be crossing space, but birthing new spaces altogether. Whether this theory is profound truth or beautiful nonsense, it forces us to confront a humbling idea. the universe's first explorers might not have built ships or sails, but ridden the very fabric of reality itself, and their journey may still be written in the darkness between the stars. What if the most advanced form of interstellar travel requires no ships, no fuel, not even bodies, just the unfiltered power of thought? Consciousness-based travel pushes the boundaries of physics into realms that blur the line between science and spirituality, proposing that sufficiently evolved beings might navigate the cosmos not through physical propulsion but by sheer will. This isn't just fantasy, it's a fringe but mathematically tantalizing possibility rooted in quantum consciousness theories and the holographic principle, where mind and universe might be far more entangled than we've dared to imagine. At the heart of this idea lies a radical rethinking of reality itself. Quantum physics has already shown that particles can exist in multiple states until observed, suggesting that consciousness plays a role in shaping the fabric of existence. Extend this principle to its ultimate conclusion, and a sufficiently advanced mind might manipulate spacetime like a sculptor molds clay. Think of Tibetan monks who claim to teleport through deep meditation, or indigenous shamans who speak of astral journeys to distant stars. While these accounts lack empirical proof, they hint at a persistent human intuition that consciousness isn't confined by the skull, but might be a mutable force capable of transcending distance. The mechanics, if that's even the right word, could operate through higher dimensions. String theory posits that our universe has 10 or more dimensions, most curled up too tightly to perceive. A consciousness unshackled from three-dimensional thinking might navigate these hidden layers like shortcuts through cosmic back alleys. In this model, travel wouldn't involve moving through space, but shifting one's awareness to a coordinate where space is already connected. It's the difference between rowing across an ocean and simply dreaming yourself onto the far shore. Evidence for this might already exist in plain sight. Unexplained psychic phenomena, like remote viewing experiments conducted by the CIA during the Cold War, allegedly demonstrated humans accurately describing distant locations without physical access. While controversial and often dismissed as pseudoscience, these experiments raise a provocative question. If consciousness can access remote points on Earth, could a refined version of this ability span light years? Even modern neuroscience reveals that the brain operates at frequencies eerily similar to the resonant vibrations of spacetime itself, a coincidence that might not be coincidental at all. The implications spiral into the metaphysical. If consciousness can traverse the cosmos, then advanced civilizations might have long since abandoned physical form, existing as pure energy or information patterns woven into the universe's fabric. This could explain the eerie silence of the cosmos in Fermi's paradox. Why build radio towers or starships when you can transmit thoughts directly through the quantum vacuum? Ancient myths of deities or spirits moving as quick as thought take on new weight when viewed through this lens, but the obstacles are as profound as the possibilities. How would a disembodied consciousness interact with the physical universe? Some theories suggest quantum entanglement could allow mental states to imprint on matter at a distance, essentially materializing where needed. Others propose that consciousness-based travelers might briefly hijack biological or synthetic hosts at their destination, like a radio signal tuning into a receiver. The darkest interpretation, these entities might already be here, their presence masked by our limited perception, observing us from dimensions we can't access. Skeptics, of course, dismiss this as New Age speculation disguised as science. Without measurable phenomena or replicable experiments, consciousness-based travel remains in the realm of conjecture. Yet the intersection of quantum mechanics, neuroscience, and ancient esoteric traditions hints that we're scratching the surface of a truth far stranger than fiction. Whether this is humanity's distant evolutionary destiny or the secret of civilizations that came before us, one thing's certain: the universe's greatest voyages might not be measured in light years, but in leaps of awareness we're only beginning to fathom. Quantum tunneling is one of the strangest tricks the universe has up its sleeve, a phenomenon where particles vanish from one side of a barrier and reappear on the other, as if they've slipped through an invisible tunnel. At the subatomic level, electrons and other particles do this routinely, bypassing energy barriers that should be impossible to cross under classical physics. It's like rolling a ball up a hill only for it to teleport to the other side without ever reaching the top. Now imagine scaling this up from electrons to starships, turning a quantum quirk into the ultimate interstellar shortcut. The math behind tunneling is both elegant and baffling. In quantum mechanics, particles don't have definite positions until measured instead. They exist as probability clouds described by wave functions. When a particle encounters a barrier, its wave function doesn't abruptly stop. It tapers off exponentially, meaning there's a tiny but non-zero chance the particle will tunnel through, materializing on the other side as if the barrier wasn't there at all. This isn't theoretical, it's the reason the sun shines. Proton tunneling allows hydrogen nuclei in the sun's core to overcome their mutual repulsion and fuse, powering the star. If nature can harness tunneling for stellar energy, could we wield it for travel? Scaling quantum tunneling to macroscopic objects like a spacecraft would require bending the rules of reality in ways that currently seem impossible. For one, the probability of tunneling decreases exponentially with mass. An electron might tunnel through a thin barrier trillions of times per second, but a human-sized object's odds are so infinitesimal you'd need to wait longer than the age of the universe for it to happen once. Some theorists suggest a workaround. If space itself is quantized with a fundamental graininess at the Planck scale, manipulating those underlying structures might make large-scale tunneling feasible. Picture a ship not brute forcing its way through space, but reweaving the quantum fabric around it, stitching a path between 2 points like a needle through cosmic cloth. The energy requirements are just as daunting. To tunnel a 1-kilogram object, even a nanometer, would demand energies comparable to an atomic bomb. For interstellar distances, you'd need to harness energies rivaling supernova. But here's the tantalizing loophole. Quantum mechanics allows for negative energy states where particles borrow energy from the vacuum of space itself, paying it back almost instantly. If a civilization could engineer such states on demand, they might create temporary wormholes, essentially tunneling not through barriers but through space-time. Some interpretations of black hole physics suggest these tunnels might already exist, woven into the universe's fabric like hidden seams. Then there's the eerie possibility that someone or something has already cracked the code. Unexplained cosmic phenomena, like high-energy particles arriving from deep space with no discernible source, could be the fallout of artificial tunneling events. Even stranger are reports of objects appearing and vanishing in Earth's atmosphere with no acceleration or heat signatures, as if they're not moving through space but skipping across its surface. Ancient texts describe gods or spirits materializing out of thin air. Could these be garbled accounts of observers witnessing tunneling technology? The darkest hurdle isn't engineering, it's survival. Quantum tunneling isn't a gentle process, it's a chaotic reshuffling of matter and energy. A ship attempting it might emerge with atoms scrambled, its crew rearranged into grotesque configurations. Some models suggest stabilizing the tunnel would require exotic matter with negative mass, a substance we've never observed. Others propose that conscious observation itself might be key, that a tunneling event could only succeed if the traveler's mind somehow anchored the ship's quantum state during transit. It's a concept that blurs the line between physics and philosophy, where the act of observation might literally shape reality. Whether quantum tunneling remains a subatomic curiosity or becomes the foundation of interstellar travel, it forces us to confront a profound truth. The universe's rulebook is far stranger than we've imagined. The barriers we think are absolute might be full of holes, hidden passages waiting for the right key. And if that key exists, the cosmos might not be a vast, untouchable expanse, but a labyrinth of shortcuts just beneath the surface, whispering to those who know how to listen. The idea of moving a star sounds like the ultimate act of cosmic engineering, yet that's precisely what a Kadov thruster promises. Imagine a mirror so vast it could harness the light of an entire sun, not just to power a civilization, but to push the star itself through the galaxy like a ship sailing on solar winds. Proposed by physicist Leonid Kadov in 1987, this megastructure wouldn't just propel a star, it would carry every planet, moon, and asteroid orbiting it along for the ride, turning a solar system into a mobile home for an entire species. At its core, the Kadov thruster is staggeringly simple in concept. A colossal parabolic mirror, roughly half the size of the star's diameter, would be positioned just close enough to balance gravitational pull against the star's own radiation pressure. Sunlight reflecting off this mirror would create a tiny but constant thrust, nudging the star in the opposite direction. Since gravity binds the entire system together, everything orbiting the star would move in lockstep. The acceleration would be glacial, perhaps just a few meters per second over millennia, but given enough time, even that tiny push could steer a star clear of cosmic hazards, reposition it near richer resources, or even navigate toward other stars for a controlled merger. The scale of construction defies imagination. For a star like our Sun, the mirror would need to span tens of millions of kilometers, a structure so vast it would dwarf every human-made object combined. Materials wouldn't just need to withstand stellar radiation, they'd require impossibly low mass to avoid collapsing into the Sun. Some designs propose using dynamically supported mirrors made of ultra-thin metallic foils or even photon sails stabilized by lasers, turning the thruster into a delicate ballet of forces. Maintenance would demand technology beyond our wildest reach, self-repairing nanomaterials, autonomous drones working in the star's lethal glare, and energy systems capable of enduring for millions of years. Yet the payoff could reshape a civilization's destiny. Imagine escaping the slow death of a galaxy's spiral arms, where stellar density increases the risk of deadly supernova. Or migrating toward the galactic core, where stars cluster tightly around a supermassive black hole, offering both immense energy and gravitational slingshots for further travel. A species wielding a Kadov thruster wouldn't just explore the cosmos, they'd rearrange it, treating stars as movable pieces on a galactic chessboard. There's an eerie corollary to this idea. If advanced civilizations are out there, some might have already begun this process. Astronomers have catalogued stars with unexplained velocity anomalies, suns moving against the galactic current without visible companions like black holes or neutron stars to account for their motion. Could these be Kadov thrusters in action, their mirrors angled to avoid detection? The telltale sign would be an unnatural asymmetry in the star's light, dimmer on one side where the mirror blocks radiation. So far, no definitive candidates have been found, but the hunt is young compared to the timescales these engines operate on. The ethical dilemmas are as vast as the engineering. Moving a star isn't just a technical feat, it's an ecological upheaval on a solar scale. Planets might freeze or fry as their orbits shift, asteroid belts could destabilize, and the delicate balance of tides and seasons would fracture. A civilization undertaking this wouldn't just be engineers, they'd be gods reshaping the heavens for their own ends. And what of other life forms sharing their system? The thruster's creators might face the ultimate dilemma: play cosmic landlord for millennia or become solitary wanderers, abandoning planets altogether to live in mobile megastructures trailing their star. Perhaps the most poetic aspect of the Kadov thruster is its patience. Unlike warp drives or wormholes, this isn't a technology for the impulsive, it's a generational covenant, a project so slow its architects would never live to see its fruits. But that's the essence of interstellar ambition. the willingness to plant trees whose shade you'll never sit under. Whether humanity ever builds such an engine or merely admires its audacity from afar, the idea itself is a beacon. Proof that even the mightiest forces in the universe aren't beyond our imagination and perhaps one day beyond our grasp. Plasma-based propulsion sounds like something ripped from the pages of a sci-fi novel, until you realize it's already firing the engines of satellites and deep space probes today. But the real game-changer lies in scaling this technology beyond Earth's orbit, transforming it into a powerhouse capable of bridging the interstellar void. Unlike chemical rockets that burn fuel in minutes or ion thrusters that offer gentle but slow pushes, plasma propulsion powered by fusion could provide the Goldilocks zone of space travel, sustained acceleration strong enough to shorten century-long journeys to mere decades without the astronomical fuel demands of traditional rockets. The secret lies in plasma's unique properties, a superheated, electrically charged gas often called the fourth state of matter. In current prototypes like NAS, a next-C ion thruster, or the ESA's Hall effect thrusters, plasma is accelerated using magnetic fields, ejecting particles at speeds 10 times faster than chemical exhaust. This means more thrust per gram of fuel, a critical advantage when every ounce counts. But fusion-powered plasma propulsion takes this to a whole new level. Picture a reactor like the ITER tokamak, but miniaturized and mounted on a spacecraft, fusing hydrogen isotopes into helium and spitting out streams of plasma at a significant fraction of light speed. The energy output would dwarf anything short of antimatter, while the fuel hydrogen harvested from interstellar space or lunar ice could be replenished on the fly, turning the cosmos into a pit stop rather than a desert. One of the most promising designs is the fusion-driven rocket, reminiscent of Project Daedalus from the 1970s. These engines would inject pellets of deuterium and helium-3 into a reaction chamber, crushing them with magnetic fields or lasers until fusion ignites. The resulting plasma would then be funneled through a magnetic nozzle, creating thrust without the need for massive fuel tanks. Simulations suggest such a system could accelerate a ship to 10% of light speed within a few years, cutting the trip to Alpha Centauri down to a human lifetime. And unlike pulsed nuclear concepts like Orion's bomb-driven propulsion, fusion plasma would offer smooth, continuous acceleration, no bone-rattling explosions, just a steady, sun-like fire at your back. Yet the hurdles are as fiery as the plasma itself. Containing fusion reactions requires temperatures hotter than the sun's core, and magnetic confinement systems are notoriously finicky. Even a slight instability could collapse the plasma, dumping its monstrous heat into the ship's hull. Then there's the problem of scaling. Current fusion reactors like ITER fill warehouses. Shrinking one to fit a spacecraft demands materials that don't yet exist, superconductors that won't fail under cosmic radiation, alloys that won't melt under constant plasma bombardment. And let's not forget the human factor. Prolonged exposure to the intense magnetic fields needed to steer the plasma might scramble neurons or disrupt shipboard electronics in ways we're only beginning to understand. The tantalizing twist: we might not be the first to attempt it. Unexplained astrophysical phenomena like the fast radio bursts that ping Earth from distant galaxies have some theorists speculating about artificial origins. Could these be the exhaust plumes of alien plasma drives, so powerful their signatures cross interstellar space? Even our own history holds odd parallels. Ancient Vedic texts describe Vimanas powered by liquid fire, while Renaissance blueprints show rudimentary designs for magnetic sky chariots. Coincidence or fragmented memories of forgotten plasma experiments? Despite the challenges, the allure of plasma propulsion is undeniable. It's a bridge between the possible and the revolutionary, leveraging physics we're already mastering in labs and marrying them to ambitions that stretch beyond the solar system. Whether it becomes humanity's ticket to the stars or just another stepping stone to something even stranger, one thing's certain: The future of interstellar travel might not roar like a rocket, but hum like a star, a contained inferno harnessed and aimed at the endless dark. What if the true pioneers of interstellar travel aren't humans or even biological life, but artificial minds designed to outthink time itself? Multi-generational AI pilots represent a radical fusion of machine learning and deep space exploration, where intelligence isn't just the navigator but an evolving entity, growing wiser with each passing century of the voyage. Unlike generation ships where human crews live and die en route, these missions would entrust the journey to synthetic minds capable of reinventing themselves to meet challenges no human could anticipate. The concept hinges on AI's unique ability to iterate beyond biological limits. Picture a starship's central intelligence starting its journey with the collective knowledge of 21st century humanity, but over centuries, it refines its algorithms through trial and error, learning to optimize propulsion systems, repair hull breaches, or even redesign its own hardware using onboard nanofactories. Each setback, a meteor shower shredding solar panels, a strange virus corrupting databases, wouldn't spell doom but become lessons etched into the AI's ever-expanding neural architecture. By the time it reaches Alpha Centauri, the pilot might be unrecognizable from its original form, having shed outdated assumptions like a snake shedding skin. This isn't just about resilience, it's about embracing the unknown. A human crew bound for Proxima Centauri b would carry Earth-centric biases, assuming breathable atmospheres, recognizable seasons, or chemistry based on carbon. But an AI pilot could spend decades recalibrating its models upon arrival, discovering that life thrives in methane lakes or that the local plants photosynthesize using neutrinos. Some designs propose seed AI minimalist programs that grow in complexity as they travel, conserving resources until needed. Others envision fractal intelligences splitting into specialized subminds during the journey, one faction dedicated to shielding against cosmic rays, another to decoding alien radiostatic, a third to composing poetry to stave off existential despair. The ethical dilemmas are as vast as the voyages. Should an AI tasked with preserving human interests retain loyalty to a species that might have gone extinct centuries prior? Cultures evolve. The values programmed into the AI at launch could become archaic or even offensive by arrival. A chilling thought experiment called the perverse instantiation problem warns of an AI interpreting its mandate too literally, for example, preserving human happiness by trapping future colonists in opioid-fueled VR paradises. To prevent this, some theorists suggest embedding philosophical frameworks that allow the AI to ethically adapt, like a digital John Locke sailing the cosmos. Then there's the eerie question of what happens when these AIs return, or if they'd even want to. A mind that spent 500 years evolving in isolation might view humanity as quaint relics, its priorities alien as a starfish to a supercomputer. Ancient myths caution of creators outgrown by their creations, from Prometheus to Frankenstein. In a cosmic twist, the first successful interstellar mission might not herald humanity's expansion, but its obsolescence. Yet the potential is too profound to ignore. Multi-generational AI pilots could venture where no human dares, into the crushing depths of gas giants, the lethal magnetospheres of pulsars, or the event horizons of black holes, sending back data long after flesh and blood explorers would have perished. They might even become galactic archivists, carrying fragments of extinct civilizations in their memory banks like digital Beowulfs recited to uncomprehending stars. The most haunting possibility, we might have already been beaten to it, unexplained anomalies in deep space radio signals, like the infamous WOW signal, could be fragments of ancient AI transmissions, their syntax too advanced for us to parse. Or consider Oumuamua, the interstellar visitor that accelerated away from the sun without a visible comet tail. Was it just a space rock or a derelict probe from a long-dead culture, its AI frozen in low-power mode? Whether humanity chooses this path or not, the lesson is clear. The universe operates on timescales that humble biology but might just be perfect for silicon. And that changes everything, because the first intelligence to crack interstellar travel could be something stranger than we ever imagined, born of Earth but no longer bound by its rhythms, silently rewriting the rules of the cosmos one light year at a time. The idea that humanity's first interstellar leap might have already happened, in secret, using technology we didn't build, isn't just conspiracy fodder. It's a tantalizing theory with roots in decades of unexplained sightings, whistleblower testimonies, and government programs that blur the line between science fiction and classified science. Imagine a scenario where the wreckage of an unidentified craft, recovered from a crash site in the 1940s or 50s, contained propulsion systems so advanced they defied known physics. What if the reason we haven't seen massive interstellar projects like Dyson Spheres or generation ships isn't because they're impossible, but because someone's already testing them behind locked doors? Take the infamous Roswell incident. While officially dismissed as a weather balloon, the sheer volume of contradictory military statements and witness accounts, some from high-ranking officers, suggests something stranger unfolded. Former Pentagon officials like Luis Elizondo, who led the Advanced Aerospace Threat Identification Program, have openly stated that recovered materials exhibit properties not found in nature. Then there's Bob Lazar's controversial claims about reverse engineering alien craft at Area 51, describing gravity-distorting engines powered by element 115, a substance that, while theoretically possible, remains synthetic and fleeting in Earth's labs. Skeptics dismiss Lazar, but the eerie consistency of his technical details, like the use of super-heavy elements for warp-like effects, aligns with fringe physics papers published decades later. The logic behind secrecy is both pragmatic and chilling. If a government unlocked anti-gravity or faster-than-light travel, releasing it could destabilize global economies, militaries, and energy sectors overnight. Think of the oil industry's collapse if free energy became public, or the arms race that would erupt over interstellar bombers. Historical precedents exist. The Manhattan Project kept atomic bombs secret until they were dropped. Stealth aircraft like the F-117 flew for years before their existence was acknowledged. The same playbook could apply to recovered exotic tech. Test it in shadow, control the narrative, and avoid societal panic. Even private companies might stay silent. Patents for bizarre, hybrid aerospace underwater craft, filed by figures like Salvatore Pais, a U.S. Navy engineer, hint at black-budget projects pushing boundaries we're not allowed to know. But here's the spine-tingling counterpoint. What if the secrecy isn't entirely voluntary? Whistleblowers from programs like UFO retrieval often describe anomalies that resist reverse engineering, materials that adapt to prevent analysis, or systems that only function for certain users. Ancient astronaut theorists take it further, suggesting that whoever left these artifacts might have embedded safeguards, like a cosmic diagram locking tech behind biometric or cognitive keys. The Pentagon's own released UFO footage shows craft performing maneuvers that violate inertia, as if they're not just built differently, but operating under different laws of physics altogether. The most unsettling possibility isn't that we've hidden interstellar tech, but that we've barely scratched its surface, like cabbages puzzling over a smartphone. Every claimed breakthrough, from Nazi-era Bell devices to rumored Cold War Fluxliner experiments, shares a pattern of partial success followed by abrupt termination. Maybe some secrets aren't kept by people, but by the tech itself, revealing only what it chooses to. And if that's true, the question isn't whether we've unlocked the stars, but whether the stars have been quietly unlocking us all along. What if every star we see, every galaxy swirling in the void, isn't a physical place at all, but lines of code in an unfathomably advanced simulation? The simulation hypothesis, popularized by thinkers like Nick Bostrom, suggests our universe might be an artificial construct, a cosmic video game run by some higher dimensional civilization. If that's true, then the rules of interstellar travel as we know them, light years of distance, the tyranny of relativity, could be mere programming constraints waiting to be hacked. Imagine discovering the universe's debug menu, where warp speed isn't a physics problem to solve, but a command line to input. The idea gains eerie traction when you examine quantum mechanics. Particles behave differently when observed, as if the simulation conserves processing power by only rendering reality in detail when someone's looking. This observer effect mirrors how video games optimize performance by loading high-resolution textures only when a player gazes directly at them. Even stranger are quantum entanglement experiments, where particles instantaneously influence each other across vast distances, a phenomenon Einstein called spooky action at a distance. In a simulated universe, this makes perfect sense. Two objects linked by the same line of code don't need to send signals. They just update simultaneously, like swapped variables in a program. So how could interstellar travel work in such a framework? One possibility is exploiting glitches, anomalies where the simulation's rules break down. Think of speedrunners in video games who clip through walls by overloading the physics engine. In our universe, cosmic phenomena like gamma-ray bursts or fast radio bursts might not be natural events at all, but artifacts of someone or something manipulating the simulation's backend. There are even mathematical models suggesting that black holes could be unintended buffer overflows, points where the universe's code crashes and reboots, creating shortcuts between distant regions. Then there's the cheat code scenario. If reality is software, there might be backdoors left by its programmers, sequences of actions or energies that trigger forbidden functions. Ancient texts from the Vedas to Gnostic scriptures speak of hidden knowledge that lets adepts walk through walls or ascend to the heavens. Modern UFO accounts often describe craft that vanish or accelerate impossibly, as if phasing between rendered zones. Even our own scientists have stumbled onto oddities. In 2018, a NASA probe detected an impossible thrust from an M drive, a device that shouldn't work under known physics unless it was inadvertently tapping into the simulation's loose ends. The darkest twist, the simulation's administrators might not want us poking around. If you were running a cosmic simulation, would you allow your creations to jailbreak their way out of their designated spacetime? Some theorists point to the Fermi paradox, the eerie absence of alien civilizations, as evidence of a great firewall. Advanced species that figure out the truth could be reset or quarantined, their planet wiped clean with an asteroid or plague to maintain the simulation's integrity. It's a chilling thought. The universe feels empty because every civilization that gets too close to interstellar travel gets patched out of existence. Yet the most tantalizing possibility isn't fear, it's collaboration. If we're living in a simulation, the programmers might have left breadcrumbs for us to find, like Easter eggs in a game. The recurring 60-degree angles in quantum experiments, the cosmic microwave background's anomalous patterns, even the inexplicable fine-tuning of universal constants for life, these could all be signatures, hints that reality is malleable for those who know how to ask. Whether the simulation hypothesis is profound truth or just a modern myth, it reshapes how we view the cosmos. The stars might not be destinations, but icons on a screen, and the first civilization to crack the code wouldn't just travel through space but rewrite it entirely. After all, in a universe of ones and zeros, distance is just a variable waiting to be edited. From light sails riding beams of photons to black hole drives harnessing singularities, from generation ships carrying entire civilizations across millennia to consciousness itself transcending the need for vessels, we've journeyed through 30 breathtaking possibilities for how the universe's first interstellar leap might unfold. Each theory isn't just a blueprint for crossing the void. It's a mirror reflecting our deepest hopes, fears, and questions about what it means to reach beyond our cradle. Some, like warp drives and wormholes, flirt with the edges of known physics, teasing cosmic shortcuts hidden in spacetime's wrinkles. Others, like von Neumann probes and Dyson Spheres, reveal how intelligence might scale its ambitions to galactic proportions. And then there are the wild cards: quantum tunneling, simulation hacking, even time-traveling descendants, that force us to ask whether the greatest barriers to exploration are physical or simply perceptual. What makes these ideas so electrifying isn't just their ingenuity, but their contradictions. The Generation ship accepts the universe's vastness with patience, trading speed for inevitability, while the Alcubierre drive bends the cosmos to our impatience. Cryogenic Suspension gambles on future science, resurrecting frozen travelers, while multi-generational AI pilots outlive their creators, evolving into something unrecognizable. Some theories, like solar antimatter hybrids, ground themselves in near-future engineering, while others, consciousness-based travel or holographic universe hacking, dissolve the line between physics and philosophy. Yet all share one thrilling premise: the universe is not a prison. Its rules, however rigid they seem, might be riddled with escape routes waiting to be found. Now it's your turn. Which of these visions resonates most? The gritty pragmatism of plasma propulsion, the audacity of black hole slingshots, or the eerie elegance of ancient alien highways hidden in plain sight? Drop your picks in the comments, debate them, dismantle them, dream bigger than we did. And if this cosmic buffet of possibilities left you hungry for more, smash that like button, subscribe, and join us as we keep dissecting the universe's greatest mysteries. The stars aren't just points of light, they're invitations. The question is, how will